Swayam Prabha. Digital India. Educated India.
So, in the last lecture, we were looking at the design of packet column for absorption related to concentrated mixtures. And when we dealt with gas phase compositions, we derived set of equations. For example, this is what you will get for the height of the packet column. This expression basically splits into two parts, one that involves the height transfer unit, another one that involves the number of transfer units, NTU, and the HTG is defined as G by FGA, where Fg is the local gas phase mass transfer coefficient. Okay, if you want to write this in terms of K-type mass transfer coefficients like Ky and Kg, you have to use the corresponding conversion factors. In the case of NTG, this integral has to be either graphically or numerically should be done, which involves the interfacial concentrations and the concentration along the operating line. Now, suppose if I were to do the same problem using the liquid phase composition, okay, I can get a set of equations in the liquid phase compositions also. Okay, so I'll write this so that we can compare. So the same derivation can be repeated for liquid phase compositions. And you will see that the height of the column you will find this expression. So you can see that this HTG is now replaced by HTL because this will involve the liquid phase local mass transfer coefficient. And here in the gas phase, the driving force is Y minus Yi, because in absorption the operating line is above the equilibrium line. Okay, so the driving force is Y minus Yi, whereas in the case of liquid phase composition, the driving force is Xi minus X. Okay. And you can also do something similar. You can take this HTL out. And then you can define HTL as L over FLA So these are the conversion factors if you want to replace the F type with the K type mass transfer coefficients. And NTL will be the remaining term. So therefore the height of the column can be written as HTL times NTL. So this is the number of transfer units with liquid phase compositions. And this is the height transfer unit This also based on the liquid phase composition or the liquid phase mass transfer coefficient. So even though we have written these expressions for absorption, these equations are also relevant for stripping operation also. Okay. So when you do stripping operation, the changes will be that in here this term will be negative, because in the stripping the driving force is yi minus y. However, this y2 will be larger than yi. So this, because of this y1, y2 and y minus yi changing the sign, this expression will remain the same. Okay, so you can still use this set of equations for stripping. So use these equations for stripping operation. So in stripping operation, you will see this y minus yi is negative, and similarly xi minus x will also be negative, but at the same time you will see that y2 is larger than y1 and x2 also is larger than x1. Okay, so because of this, this equation remains the same if you were to do all this over. So all these equations are written with respect to the local mass transfer coefficients and the local driving force y minus yi and xi minus x. So like we did in the lean dilute mixtures, where we express the driving force with respect to the overall driving force y minus y star and x star minus x, you can do something similar here also. Okay, you can replace all the local coefficients with overall coefficients. Then all the number transfer unit and HTU, these all will become in terms of overall units. So right now these expressions are for local coefficients, either for the gas phase or the liquid phase. Now we can also write one set of equations for the overall. So if I have to use this overall mass transfer coefficient, I have to ensure that the operating the equilibrium line should have a constant slope m. Okay, only then I can relate the overall driving force with the local driving force. Okay, so if equilibrium line is a straight line, we can use overall mass transfer coefficients. So then you can write a set of equations. So now I am introducing this O here to denote it as an overall coefficient. So here you can see this mass transfer coefficient FOG is the overall gas phase mass transfer coefficient. So here you can see that I am changing the driving force with respect to the equilibrium concentration rather than the interfacial concentration. Okay, so these are the changes that you will see if you use the overall mass transfer coefficients. Okay, so now if you want to simplify this further by replacing the log mean difference with arithmetic difference, you can get this equation that y2 to y1 dy by y minus y star plus 1 by 2 ln of 1 minus y2 by 1 minus y1. So from here to here, what we have done is we have replaced the logarithmic mean driving force with arithmetic concentration difference. Then you will be able to write this in simple form. So in here you can note that I am again writing for overall coefficient, overall NTU, using the overall driving force y minus y star, and you can also write this expression in terms of mole ratios. So here it's everything is in mole fractions. You can write this into mole ratios with capital Y's. Note that this term now changes when I change the mole fraction to mole ratio unit, because I have to substitute for Y2 and Y1 in terms of the mole ratio. Then this term becomes this. So this is for the HTOG and NTOG. You can also write in terms of liquid phase composition as HTOL times NTOL, where HTOL is the height transfer unit, overall height transfer unit with respect to the liquid phase composition. So here you can see I am using overall liquid phase mass transfer coefficient, FOL. Again I am changing the driving force as x star minus x. In the local coefficients it was xi minus x. So now we are using overall coefficient, so it's x star minus x. Again here also I can replace this log mean difference with arithmetic average and I can get a simplified expression. And if I want to write this in terms of mole ratio units, that's it. Why we are not replacing which one? Okay, so you're saying, let me see, 1 minus, I will say y2 by 1 plus y2. So I'll have 1 by 1 plus y2. So this has to be, so this should be like this. Yeah, okay, good. I think somehow I made a mistake here. So okay, so this is correct. So it should be 1 plus y1 by 1 plus y2. So here similarly I would have 1 plus x2 by 1 plus x1. Okay, is it right now? Oh, okay. So one day I'm using the mole ratio now, so it should be fine. Yeah. Okay. So here I have written only expression for NTOG. I'm going to now show expression for HTOG. Okay. So there you will see that the overall coefficient can be written in terms of local coefficients only if the equilibrium line is a straight line. Okay. So in all these expressions, we have only expressed this NTOG and HTOG. So here I have written the overall F-type mass transfer coefficient. Okay, but this has to be obtained from the local coefficients. Okay, so if you remember, when we used dilute mixtures, using K-type MTCs, we showed that if the equilibrium line is straight, I can write the overall coefficients using the local coefficients. You may recall this, right? We wrote that 1 by ky, capital ky is equal to 1 by small ky plus m times kx. So this m is the slope of the equilibrium line. We can do this if the equilibrium line is a straight line. Okay. Similarly, 1 by kx is written as something like this, right? Now this is okay for k type mass transfer coefficients. And we also have to remember the kind of mass transfer we are talking about here is A diffusing through non-diffusing B. Okay, so when you have a mass transfer situation that A diffusing through non-diffusing B, then if you are talking about lean mixtures, dilute mixtures, and if the equilibrium line is straight line, these equations are valid. Okay, so now I am removing one assumption, which is I am not talking about dilute mixture, I am talking about concentrated mixture. So I am still talking about a mass transfer A diffusing through non-diffusing B, that is still there, and then I am also saying that the equilibrium line is a straight line. I am only removing the assumption that it is not dilute anymore. So now I want to write an equivalent expression like this for the F type. Okay, what would it be if I have to write 1 by FOG? This is used in the high transfer units, HTU. Okay, similarly I am using 1 by FOL for the liquid phase HTU. So what would this be? This should be written in terms of function of Fg, Fl and M. Similarly, this should be written as a function of Fg, Fl and M. We may be tempted to write an equation like this, that 1 by FOG is equal to 1 by Fg plus M by 1 by Fl, but that is not correct. Okay, because this assumption was based on the dilute mixtures, where the concentration difference, where the flux, so in this case the flux was simply written as the concentration difference. Ky into y minus yi, something like this. Okay, but in F type or with the concentrated mixture, we write the flux is equal to some Fg times ln of 1 minus yi by 1 minus y. So the expression for mass transfer rate is different for dilute mixture and concentrated mixture. When I take mass transfer rate in this form, I can use this to get the overall coefficients. We have done this in one of the lectures before. So now what do you need to do? I need to use this kind of mass transfer rate for the concentrated mixture and then get this kind of function. And you will see this is not as simple as this. It's going to be a little bit more complicated because of the fact that there is a logarithmic term. So. Okay. So now I'm not going to derive this. I'm going to give the expression for this, and in the textbook, Treble's textbook, this derivation is available. Okay, so if you want to take a look at it, you can look at it. So let me just give you the expression that 1 by FOG is written as 1 by F G 1 minus y im by 1 minus y star m plus m by FL so you can kind of compare these two expressions. For the dilute mixture, the overall coefficient can be simply written in this way, whereas when you look at concentrated mixture, where the mass transfer rate is expressed in terms of this logarithmic term, the expression for the overall F-type mass transfer coefficient involves the local coefficients, but also the concentration effects. So this is what I was saying, that the F-type coefficient will depend on the composition. Okay, so here if I go back in the derivation of these equations here, so you see that I said G is changing, but Fg also will change, but the group of terms together is found to be empirically found to be almost constant. So I can take the group of terms out, but not individually. So the fact that why this Fg or FOG depends on composition is actually shown here. Okay, so you see this y, the y 1 minus y im, this is the log mean difference of the interfacial concentration. This is the log mean difference of the equilibrium concentration. I will give the expression for this right now. So 1 minus y im is 1 minus yi minus 1 minus y over ln of 1 minus yi by 1 minus y. Similarly, 1 minus y star m So this is how these log mean difference compositions are written. Okay, and you can see that these concentration terms are also factor in the definition of overall F-type mass transfer coefficient. Okay, so now what I can do, I can actually multiply by term G by A across. So I'll get G by FOG A. Why I'm doing that is because the left hand term now is HTOG. Okay, so this equation is actually equation 5.25 A in table. You can find the derivation of this. So now I take this expression and then multiply by the term G by A. So this term now I can define as HTOG. This is a height equivalent of overall gas transfer unit. And this term is HTG. This is a gas phase height transfer unit. And this term remains as such. So how can I replace this in terms of HTL? How is HTL defined? L by FLA. FLA is there, but L is not there. So I'm going to multiply and divide by L here. Okay. So then I can group these terms as HTL. What is this mg by L term? 1 by, this is absorption factor A. Okay. Then the remaining terms are as such. So this is the expression for HTOG. Yeah. 1 minus? Yeah. It should be star M. Is it right? 1 minus, where is why 1 minus x is coming? Is there any other is there any simplification is possible here from here onwards? So this expression is valid for both phase controlling. Okay, if the liquid phase is also controlling, if the gas phase is also controlling, this expression is exact. So you can use this. Okay, which means you have to get the HTG, you have to get the HTL, and from there you can get the total overall HTOG. We already know how to calculate NTOG from here. Okay, so that basically completes the calculation of the height of the column. But the question is there any simplification possible from here? Okay, so let's say gas phase is dominantly controlling. Okay, gas phase is controlling. So when I say gas phase is controlling, what would you say about the slope of this equilibrium line? If the gas phase is controlling, how would you think about this equilibrium line be? So it's going to be something like very small m, right? So that means I can actually replace yi with y star. Okay, so yi is almost same as y star. The interfacial concentration and the equilibrium concentration can be very similar. Then this entire term will be just 1. They are equal. Okay, so in that case I can write HTOG is equal to HTG plus HTL by A, and this term remains. And then if you want to make one more assumption that if these mixtures are entirely dilute, then this entire term can be approximated to 1, then you get HTOG is equal to HTG plus HTL by A. This is what you would have got in the first place if you had used K-type mass transfer coefficient. Okay, so we are talking about 3 equations. Equation 1 exact, equation 2 gas phase controlling, equation 3 gas phase controlling and very dilute mixture. Okay, so these are options we have. If you want to go with the simplest expression, equation 3, okay, and the next level of sophistication is here. So this is done with respect to HTOG. So now let me also tell you about HTOL. Okay, so HTOL has the same argument. So this is the expression for HTOL. So here again you can make an assumption, if liquid phase is controlling, so this means M is very large, and this means Xi is almost same as X star. So you can write HTOL is simply HTL plus A times HTG 1 minus YIM by 1 minus X star M. And then for dilute mixtures, so next what I'll do is this entire calculation of so first of all HTOG you can calculate analytically. Okay, if you know the gas flow rate and liquid flow rate and mass transfer coefficients, you can calculate. The NTOG calculation is what a little bit tricky. So this typically involves a numerical calculation or a graphical method. So I'm going to talk about a graphical method which is slightly approximate, but is very easy, very fast to do. Okay, you can quickly do it in a graph paper. Okay, so next topic is to look at graphical method to calculate, let's say, NTOG. Okay, so first of all, how we define NTOG? This is defined as Y2 to Y1 so this is the definition of NTOG. Here this term is easy to calculate because it involves only the composition at the beginning and the end of the column. Okay, only this integral is the one that we want to calculate. So now let's talk about this particular integral alone. Okay, Y2 by Y1, this. Okay, so this expression is something that might change across the column. This Y minus Y star is the driving force available for the gas phase mass transfer, and that may vary across the column. Okay, let's say that I define a kind of an average across the column. Let's say I define an average driving force using log mean difference. Okay, so then I can write this approximately, I can write this as 1 by Y minus Y star log mean difference times dy y2 to y1. So this basically becomes y1 minus y2 by y minus y star. Okay, and this is what we say as NTOG. Of course, this term has to be added to it, but right now I'm just talking about the integral term alone. So what I have done is, graphically if I have to show what I have done, I have basically taken a problem where you may have a curved equilibrium line and you may have a curved operating line, and this is y2 x2 and this point is y1 and x1. Now these are the driving force for me. Okay, this vertical line is y minus y star, and you can see that across the column, going from the column from bottom to top, this the driving force changes. But what I'm saying is, I'm going to take the driving force at the exit and entrance, and then using this I'm going to define an average logarithmic mean difference driving force, as if the driving force is constant across the column. If that's the case, then I can calculate NTOG by this simple formula. Okay, so when I make this kind of an approximation that the driving force across a column is an average value, what I'm basically saying is I'm mapping this problem into another problem where the two lines are actually parallel. So the equilibrium line and the operating line, I'm assuming it's parallel. If I assume they are parallel, I know that the driving force is constant, and this driving force is what I'm actually assuming to be constant here. For the same y2 and y1, this is y1 and this is y2, right? And the average driving force here is kept constant. So this problem is mapped into this kind of a problem, where the actual difference in the driving force is approximated to have a constant average value across the column. Okay, so then by this formula, what we can say is the NTU that we are talking about is nothing but the number of steps I can draw here. This is 1, this is 2, and so on. So what this step mean here, if you look at this step, this is the actual concentration that is changed going from this point to this point, right? This is the actual concentration change in the operating line, that is exactly equal to the driving force available, and we call that as one transfer unit. So in one transfer unit, the actual composition change happens is equal to the average driving force available. Okay, so this entire column, you're thinking about modules. In one module, one transfer unit, if you look at the composition change, that is equal to the average driving force available. That we call as one transfer unit. Okay, so now you can see here, this is a right angle triangle. This particular step is one where the composition here is changed equivalent to the driving force here. Now when I go to this particular step, this is the second step in which the composition change from here to here is exactly equal to the average driving force, and subsequently. So if I look at this operating line and the equilibrium line, and if I consider this kind of steps, I can actually count how many number of transfer units are there going from one end to the other end of the operating line. Okay, do you follow this? Do you understand what I'm trying to say? So what I'm saying is, in an actual problem, the equilibrium line and the operating line are curved. Because of this, the driving force across the column is varying. That's what necessitates us that we have to do this integral numerically. Now let's say I don't want to deal with this constantly varying driving force. I want to redefine the driving force as a constant average value. I can do an arithmetic average, or I can do a logarithmic average. Okay, we know that the logarithmic average is better to allow the variations across. We have done in heat transfer course. Okay, based on the concentration difference or the composition difference at the end points, entry and exit, using these two composition variations, I am going to define a logarithmic mean driving force. If I assume that I can take this driving force out of the integral, then NTOG is defined as the actual composition change y1 minus y2 divided by the average concentration driving force. That's what I call as the total number of transfer units. So graphically what this can be, how this can be explained is that this problem, the actual problem, is mapped to another problem where the driving forces are constant across the column. Those are shown by this vertical black line. The actual composition is still the same, y1 minus y2, the actual composition changed. Okay. Now the total number of transfer units is nothing but the total concentration change y1 minus y2 by the driving force. Okay. So that's what this expression means. And graphically this means that I can construct this kind of steps where in each step the composition change is equal to 1 unit of driving force. So in this particular step the concentration change here is exactly same as the concentration difference or the driving force. So in terms of your packed column, if this is the entire packing you have, you may see that there is one particular section. In this particular section the concentration goes from here to here, and that in that section the concentration change is equal to the driving force available. So this is actually important for us to actually construct the number of transfer unit. So this is a kind of a model problem. We will come back to this actual problem with this understanding that a number of transfer unit actually means in one transfer unit the actual composition change is equal to the average driving force. That's the definition of one transfer unit. But in the actual column, how many such transfer units are there to achieve this entire composition change? That's what we have to calculate. Okay. So now, so let me do that. So here I'm going to just show it in a stepwise operations. So graphical method. The first step is first to draw the equilibrium line. So this is my equilibrium line, and it's not necessarily be a straight line. It can be curved also. Step 2. Draw the operating line. An operating line comes from the mole balance, and I will draw something as this. Step 3. So let me also mark these points. This is y2, this is x2, this is x1, sorry, this is y1, and this is x1. Okay. So now what we are going to do is I'm going to look at the midpoint. So find the midpoint between EL and OL. So here at this point I measure this total distance between the operating line and the equilibrium line, and I find the midpoint. The midpoint is somewhere here. Okay, and I go to some other y value and I look at this total distance and I find the midpoint, and I go here and find midpoint. So some like this you can find infinite number of midpoints here. Okay, so these are all the midpoints between the operating line and the equilibrium line, and connect these points as a line. Okay, which I will call this KB. This is K and this is B, and I draw this line. Sorry, what? Can be? It can be curved. Yeah, it can be curved. It's not a straight line. It's just a line. Okay. So you see, this is a curve. Yes, it's a curve. It need not be a straight line. Step 4. So let's say this point is J. Okay, that's the end point. So from J you go horizontally to the line KB, you measure this distance and then extend this line further equivalent to this distance, and I find this point L. such that the length between this segment and this segment are the same. So draw a line such that Jn is equal to NL. So J is the point corresponding to x2, y2. You go horizontally and meet the midpoint line KB and measure the distance, that is Jn, and continue the line subsequently and reach point L such that Jn and NL are same. Okay, so from point L, go vertically and touch the operating line at point F. So that means I am going to go vertically here and I reach point F. So this is one step, and this is called the first transfer unit. Okay, so here the step JLF is one transfer unit. And we do the same thing. From F, you will repeat as if what you did in J. That means from F, you go horizontally to the midpoint. Okay, let's say this is some G, and then measure the distance F to G, and then go subsequently to another point H, so that FG is equal to GH, and then you go vertically and meet the operating line. Okay, and you continue this until you go to the end of the operating line. So here I have shown such a way that there is only two transfer units, but in actual problem you have a very large number of transfer units. Okay, so here why we have done this is because in this approach, in one step here, the average composition is YF minus YL. This is the composition change in the operating line, and that is actually equal to YF minus YL. So YF minus YL is the average driving force for mass transfer. The actual composition change is YF minus YL. This is actually YF minus YL. Yes. So we say in one transfer unit, the composition change occurred is equal to the average driving force available in that step. Okay. This particular algorithm that I showed here will ensure approximately that each step is drawn such a way that composition change is equal to the driving force, and you can construct this until you go to the other side of the operating line, and just simply count. This is 1, this is 2, and so on. So this is a graphical way of getting the number of transfer unit. Now suppose if you want to do this for stripping operation, it need not touch the equilibrium line. So what we are saying here is the step I have drawn J, L and F. Okay, in this particular step, if you look at the operating line going from J to F, the composition change is YF minus YL, because YJ and YL are the same, because they are in the same horizontal line. So the actual composition change in one step is YF minus YL. Okay, now if you look at this distance F and L, YF minus YL, that is the average driving force, because you see this distance here is same as this distance. The vertical lines are the driving force. So this line here is same as this line by this particular construct. So in one transfer unit, we say that the composition change that is happening here is equal to the average driving force. Yeah, that's why I'm taking this midpoint. Again, this is still an approximate method. Okay, this is not exact. Okay, maybe in a couple of minutes I will also explain the same operation for the stripping operation. So this is the equilibrium line, and this is the operating line. So here what we do, the midpoint is not constructed based on the vertical difference, but on the horizontal difference. Okay, because in stripping the driving force is the x minus x star, and okay, so I will take this line and many such horizontal lines to find the midpoints, and I draw a line through those midpoints. So this is a midpoint line. So this is point J. So here I go vertically. So there we went horizontally, right? So here I went from this point, I went horizontally, but in stripping operation, you are going to go vertically from J and touch this midpoint line and go further equivalent to this distance, and then go horizontally to touch the operating line. And here this is one first unit. So here the composition change happening is, so let's say this point is F. So xf minus xj is the change in the composition in the liquid phase in one transfer unit. And what is the so from here again you can do the same thing, go vertically, touch this midpoint, and then continue further. It can go above the operating line also, it doesn't matter, and then go horizontally. So this is the second transfer unit. From here again go vertically, meet the midpoint and extend to equal distance, and then go horizontally. So this is third step, and then continue this. Okay, so here you can see the three are complete, but still the operating line is still here, so you have to add one more. So the fourth there are four transfer units, you have to round it up to a nearest integer. Okay, so in this operation also what we have done is the average composition in the liquid phase, yeah, is equal to the average driving force available in one transfer unit. And you can see in this case the step has a different size because the average driving force keeps changing. Okay, if the driving force is constant, then the steps will all have the same size, like I showed here. In this particular case where the two lines are exactly parallel, the driving forces are equal, so the steps will have the exactly same size. But in these cases where the driving force keeps changing along the column, the step size will become smaller and bigger depending upon the size of the driving force. Okay, so here you should know how to get the equilibrium line, that you know from Raoult's law, Henry's law, and etc. You know how to draw the operating line based on the mole balance equation, and once you know that, then you can do a simple step construction like this to get the NTOG or NTOL. Okay, and then calculating HTOG, HTOL straightforward, multiply these two and you will get the total height of the column. Okay, yeah, okay, so we'll stop here.